Hello everyone. Over the past several weeks, we've been discussing building cryptography whose purpose is to allow parties to communicate securely. So we've been looking at the basic problem of securing communication between two endpoints, and that has entailed all kinds of primitives and uh, tools and definitions and schemes and so on. But it turns out that there's many other kinds of problems that cryptographers like to solve that aren't about secure communication. They're about various games or objectives that have some kind of privacy component. This is a huge area nowadays with potential applications and usage for things like private machine learning and electronic cash and things like that. So here we're going to take a very brief look at this area. There are so many different elements and protocols and ideas in this area that it would take years to go through all of them. And so the best I'll be able to do is just illustrate a few of the main ones. So let's start with this scenario that you want to set up a casino that functions online. You want a very simple game where a player pays a certain amount, like $1, and the casino has a guess value, has a target value, which is a number chosen randomly between 1 and 100. The player submits a guess, and the casino simply sees if the guess matches the target. If so, there's a payoff of $200, and otherwise it just says, sorry, you failed. So we want to do this online. So the question is, if the protocol is written like this, so this is the player client and this is how the casino functions. Well, looking at this, would you play? If you found a website offering this on the internet, would you jump up and down and go and start betting? If you looked at this purely from a probability theory perspective, you would be tempted to say, yes, this is actually very lucrative. Why is that? Because you have a 1 in 100 chance of guessing the target correctly. There's 100 numbers and you submit something. But when you get it right, you have a $200 payoff. So your expected payoff is this, which is $2, and you only paid 1. So probability theory says that on the average, you get richer the more you pay. And in fact, you keep getting richer and richer. So there's got to be a catch somewhere. And that enters when we adopt the security mindset that hopefully we've been developing in this class, which is that adversarial behavior is often present. And in this particular case, there is nothing here to ensure that the casino is actually doing this, which is what it says. What if it decides to get your guess, then pick a target number which is something different from your guess and claim that you didn't win? How would you know? So you might say, well, if you played this really, really often, you would know or something. Maybe they would sometimes let you win and claim otherwise it was just luck. Very hard to tell. This situation means that if we want to take a game like this and put it online, it's not clear how to do it. Now, looking at that situation, the player, having seen the protocol, might complain and say, look, it's pretty clear that you can cheat in this protocol, so I'm not going to play that. Let's play it a different way. I pay my $1, then you pick a target, and I need to know that you really picked it properly, so you send it to me, and then I'll place my guess. And now if the guess equals the target, then I win. And that's a lot of fun for the player, but the casino just laughs. Clearly, if it reveals the target here, there's no way that the player is going to lose. It can always just guess that. So this seems kind of silly, but why are we bringing this up? Because in the end, it illustrates what's at the heart of the problem. Maybe it's a kind of a catch-22 situation. The issue is that neither player can go first. If the casino goes first and chooses its target and reveals it, then the guess can be made a function of that and the player wins. If the player chooses his guess before the target, then the casino can choose the target to be independent of the guess and the casino wins. So it looks like somehow we have a contradictory, almost impossible situation to try to resolve. Okay, but how can we get around this? Let's first think, before we get to what's shown on the slide, of what kind of might be happening in a real casino. If you imagine playing this game, I would imagine it going something like this. So the casino would begin by picking a random number t in the range 1 through 100. But it wouldn't just keep that. What it would do was write it down on a piece of paper or a card and then put that card face down on the table in front of me. Now, with that card there, I would say what my guess is. And I can just write it down or say it openly. And now the casino flips open its card, and then we see if there's a match or not. And you notice if you do it that way, neither party really has an advantage. The casino cannot change what's written on the card after seeing your guess because the card is already present face down on the table. The fact that it's face down, on the other hand, means that the player is not able to base its guess on the actual value of the target. So what we see here is a similar thing, but done somehow in a way which takes into account that the parties are not physically co-located. Maybe they're at different locations. And in this version, we use physical objects. We're going to use safes. So you go to the store and you buy a safe. And what is this? It's some metal box. You can put something in it. And by this, I'll denote that I opened it and put in a piece of paper with some value written on it. And the safe has a combination or key that can be used to open it. So what the player does is it goes out and buys such a safe. It has the combination, so it can open it. And then it puts its guess inside the safe and locks the safe. And then it ships that over to the casino by some means together with its $1 payment. The casino gets the safe, and then it picks its target value at random from 1 through 100 and sends that over to the player. And now the player sends the casino the key to open the safe or combination. And the casino then opens the safe and extracts the guess. And then if the guess equals the target, it returns the payoff, and otherwise nothing. So that's how a physical version of the protocol would run. And now if we look at this, we see that it kind of works. Why is that? Because the first thing we worried about is the casino chooses this t not at random but as a function of the guess, in particular to exclude the guess. It can no longer do that because it doesn't know what the guess even is. It doesn't have the key to look inside the safe, so it doesn't know what it is. On the other hand, we were worried that the player might choose its guess as a function of the target if the target was sent first in the clear. And the reason that's avoided here is that the safe has already committed to the guess value. It's too late for the player to change its contents after seeing the target. So whatever this key opens is what it put in the safe prior to seeing the target, so the contents can't depend on it. So neither G nor T can be made to depend on each other, and so we have a decent protocol. And of course, at the end of that, if it really works, you would expect that the payoff changes. It's not going to be $200 because the casino would lose a lot of money. Now, we're interested in implementing this online, and we can't ship safes around. So what we'd like is to use some of our crypto. We'll explore some tools to do that called commitment schemes. But before we do that, we could write down one very concrete rendition of a final protocol. So it would do the following. The player would pick a random string, say of 128 bits, and it would hash that with some SHA-256-like hash function together with its guess. And that's effectively the safe. We will, in our language, call it a commitment, but compared to the prior slide, it plays the role of the safe that contains the guess. that gets sent to the casino. Looking at that, the casino doesn't know what the guess is because all it sees is this hash value. It now picks its target value at random from 1 through 100 and sends that over in the clear. Now the player has to open this safe. The way it does that is it just provides the inputs to the hash function, the G and the K. And the casino can check the opening by making sure that the hash of those two things really is the C it received earlier. And then it sees if the player won or not. If the guess equals the target, then the player won with a reasonable payoff, and otherwise it lost. And studying these things, what we'll see is that this effectively has the properties we got from those physical safes. And we will encapsulate those properties now in a primitive we call a commitment scheme. We'll look at definitions and constructions of that and eventually kind of wind our way back to this particular protocol. So as usual, when we have a new primitive, we start with some syntax. So a commitment scheme is specified by 3 algorithms, one called P for parameter generation, one called C for commitment, and one called V for verification. Now it's supposed to represent these safes, but it does so in a way that's maybe a little bit indirect. The purpose of the parameter generation algorithm is to just produce some information that might be useful for the rest of the scheme. Often this is nothing, so it will be the empty string, but it might be something like the description of a group of some prime order or a generator of a group or something like that. Now the commitment algorithm takes that and it also takes a message M. The message is whatever you want to commit to, which in our example would be the player's guess. The player is the one who runs the committal algorithm. The committal algorithm is effectively the safe, but more precisely, it's the safe creator. You can think of it as the entity that makes the safe, and C, the committal, is actually the safe itself. This committal is what contains the message. What about the decommittal key? Well, the safe creator outputs that along with the safe. So this creator takes the data and says, here's the opening key, and here's how I've encapsulated your data, and you can now open it later with this key. So the player who runs this gets both these objects and can then ship this over to the casino. The final piece of algorithmic feature that's provided by commitment scheme is a verification algorithm. That will take the message, the committal or safe, and the combination or key, and check that they match up. So its job is to simply say, okay, I agree that this committal corresponds to this message and this key. And if so, then it outputs 1, otherwise 0. And so here is the way you map it back to our prior example. So let's explore some properties, security properties that we want from this committal scheme with an eye to implementing this casino example. So there are 2 properties, and the first is called hiding. What hiding means is that when you get the safe, which is the committal, also perhaps called the ciphertext, the C value, it doesn't actually tell you anything about the contents. The contents M, the message, which in our example is the guess, remains hidden. So now what does that mean a little bit more precisely? Suppose I take a certain message and I run the committal algorithm with these public parameters. That algorithm is randomized, so it's potentially going to use coins. And formally, as per the prior picture, what it outputs is not one thing but 2 things. It outputs a committal and it outputs this key. When we say that the committal doesn't reveal the message, I mean that you get the C value. You don't get the K value, just the C value, and you're trying to figure out M, and you should fail to do that. So that's a fairly sort of natural property reflective of many things we've seen before. The other one is a little more subtle in terms of mapping to the application, and it's called binding. What makes it more interesting is that it's kind of obvious that a safe has the hiding property. A safe is indeed designed to make sure the contents are not revealed if you don't know the key. But safes also have a binding property, and that's not something we usually recognize or name. So what does this property say? It says that an adversary is trying to create a weird safe C. This safe has the property that there are actually two combinations that open it. And depending on which combination you use, the contents are different. It's as though you could somehow have two compartments in a safe, have different things in each, and then supply a key that would open one of them or the other depending on what you wanted. And security says you can't actually do that. So now let's translate it to the formalism. We have our commitment scheme with its three algorithms. And what the adversary is trying to do is find a single committal and two messages and two keys. What should be true is that if you tell the adversary, here's my committal, here is the first message and key, do they work? Are they consistent? Does it look like this was produced from these two? The verification algorithm is supposed to determine that, says, oh yes, it looks fine. Then you give it with the same committal, the other message and the other key. And the verification algorithm again says that's fine. And whenever this happens and the two messages are not the same, we have a problem. We call that a violation of binding. Okay, so now that we have that, let's see how we can fit that back to our application. So the way it would work is that the player runs the committal algorithm. Everyone knows the parameters, and the message it uses is its guess value G. And it gets a committal, and it gets the opening key. It stores the opening key locally, and it sends the committal across. The casino stores the committal, picks its random guess, and sends that over in the clear. Now the player opens. What does it mean to open? It says, here's the guess I claim is in this safe or underlies this committal. Here's the opening key so that you can check my claim is correct. So the casino will run the verification algorithm on the parameters, the committal, the guess, and the key. And if that says yes, it's okay, and then it'll go and check whether the guess was actually a winning one, and if so, the player gets a payoff, otherwise it gets nothing. And the hiding property ensures that the casino here is not able to cheat, while the binding property ensures that the player is not able to cheat. So hiding says the casino can't pick T as a function of G because C doesn't reveal anything about G. Binding says that the player can't pick G as a function of T because that would correspond to two different ways to open this fixed committal. So now to examine specific committal schemes, which are actually very popular objects in cryptography, let's just go ahead and formalize these hiding and binding requirements. So now for a little bit of time, we have shifted gears away from that specific casino example to the study of this primitive commitment schemes. So take some commitment scheme with its three algorithms, and we have a game for hiding parameterized by the scheme. The initialize procedure runs parameter generation to get some parameters and returns that. And it also internally picks a bit B called a challenge bit. Then there's a procedure which we call left or right because we're capturing privacy, and we're going to effectively use exactly the same idea as encryption, that there's going to be two messages submitted. One will be encrypted, and it's up to the adversary to figure out which one. So the game selects the bth of the two messages, either left if B is 0 or right if B is 1. And it then runs the committal algorithm on that message. This will give it a committal, but also this key. The key is ignored. What's returned to the player is, or adversary here, is only the committal. And from this, the adversary is supposed to figure out the value of this bit B. So it trundles along, and eventually maybe it thinks it has that value. So it outputs that or calls finalize and submits a guess. It says, this is what I guess B prime is my guess to be, either 0 or 1. And if the guess is correct, then the game returns true, otherwise false. And so the adversary wins if it simply figures out whether this was the left or right message being committed to. Now, when we've in the past written IND-CPA style games, we've actually written two games, left and right, and viewed the advantage as the difference of the probability of the adversary returning 1 in the two games. Here, it's being done a little bit differently and more compactly. We've put the choice of the games inside and thereby turned the two games into one game. But it's effectively equivalent. You do, however, have to notice that the advantage has to be slightly reformulated and adjusted. The reason for that is that the adversary can always win with probability of half. That's very easy. It can output B prime, let's say always 0. Since B is 0 with probability of half the time it'll win. But that doesn't mean anything. So the advantage adjusts for that. It multiplies the probability of winning by 2 and subtracts 1, because now if this probability is a half, the advantage is 0. So we have our definition of the advantage and we interpret it as usual. What's the binding game? The game is somewhat simpler because there's no non-trivial exported oracle. So it says that you take your scheme and the initialized procedure of the binding game associated to that scheme begins by running parameter generation. That'll return parameters and the adversary gets that. And then the adversary's job is to simply create a committal and two messages and key pairs that open it. And when it does that, it just outputs them and then finalize checks if it works. So what does it mean that it works? It runs the verification algorithm of the scheme with this committal and the first message key pair. Then it does the same with the same committal, but the second message key pair. And victory for the adversary means those are both accepting. So both those bits are a 1. But additionally, the messages are different. So this has violated binding in the sense that the committal didn't bind the creator of it to a unique value of the message. There were two possible messages that underlay it. So the binding advantage of A is simply the probability that it wins. Okay, so now we have definitions for commitment schemes. We could ask how we can build them. Well, we have tons of crypto tools, so we can start by trying to exploit them. And one natural thing to try is symmetric encryption. Why is that? Because ultimately a committal is hiding the message. So it looks like there's some encryption going on. So let's do it this way. I'll start with a symmetric encryption scheme with its 3 algorithms. If you want to think of an example, it's like CBC or counter mode of AES. And I'm now going to build a commitment scheme, which means I have to tell you how all 3 of these algorithms work. Parameter generation simply returns the empty string, so nothing non-trivial going on there. How do I commit to a message? Well, effectively, I want to encrypt the message so that it's kept private. But here, there isn't any key, at least so far. While an encryption algorithm takes as input a key, the committal algorithm doesn't. But the way we get around that is we just pick the key inside the algorithm. So it picks the key at random from this key space or key generation algorithm, and then it encrypts the message under that key to get a committal. And the committal in this case is a ciphertext for this encryption scheme. It returns the ciphertext or committal, and this committal algorithm is supposed to also return this key, so it also does that. How do you verify? Well, when you verify, you have a committal, a claimed message, and the claimed key. So what you could do is you could decrypt the ciphertext with this key using the decryption algorithm here and see if you get back the message. And if so, you say, okay, that's good, they match up. And otherwise you say, no, they don't match up. Okay, those are the algorithms. So we now have an example scheme and we can ask, is it secure? Meaning, is it hiding and binding? So if we look at it for those purposes, we see that hiding works quite naturally and obviously. The reason is that the committal is just a ciphertext under a key that the adversary knows nothing about. In the hiding game, the adversary gets this committal, it doesn't get the key, and is trying to figure out whether this committal was created by applying the algorithm to M0 or to M1. But that's exactly the IND-CPA game. So it translates very nicely. And that's indeed why we went this route. The difficulty is the other side doesn't work at all. So there the goal is for an adversary to violate binding is to find a ciphertext and two messages and two corresponding keys such that this same ciphertext decrypted with the first key gives the first message and decrypted with the second key gives the second message. But nothing we've ever asked for in encryption says that that isn't possible. It's just not something we cared about or came up in the encryption context. So if all I know is this is a 9DCPA scheme, there's just no reason to think something like this holds. Furthermore, it really actually doesn't hold. If you take any particular scheme we study, like cipher block chaining or counter mode or whatever, you'll see that it's quite easy to come up with attacks which violate binding. So this kind of half worked, but we didn't really get there. Still, we're going to try something along the same lines. We're going to just switch from using symmetric encryption to using asymmetric. But we're going to do that in a little bit of a different way. And to do that, we first need a little bit of notation or a closer look at what it means for encryption schemes to be randomized. So let this be an asymmetric encryption scheme, maybe some RSA or discrete log-based things. Now, usually we write encryption like this. It's a randomized operation. Given the public key and message, it returns a ciphertext. But underlying that, what's happening is that it picks something at random and then computes the ciphertext as a function of that something and the message. So we want to make that explicit. What we do is we consider a space from which certain choices of random objects are made. That space may depend on the public key. And we write this process now as saying pick that something at random, and then think of the encryption algorithm now as taking the message and this other object. And the idea is that this change in notation is done in such a way that these two processes are equivalent. So whether you write these two lines or these two lines, it's identical. You can see that in an example. So if you look, for example, at the simple RSA scheme, I claim that the space of coins associated to the public key N and E is Zn star. Why is that? Because if you look at the encryption algorithm, what it does is it picks k at random from Zn star, and then it does stuff. It creates k to the e and puts that in the ciphertext, and it hashes k with some hash function and adds the message and puts that also in the ciphertext. So if I now give e this argument k, what it does is these three steps. And then if I look at it this way, the whole thing becomes equivalent to all of this. Right? So it's just a refactoring of how public key encryption works. So why do we want this? Because here's how I want to create a commitment scheme from an asymmetric encryption scheme. So I take the ladder as given, I assume it's signed DCPA, and now when I create my commitment scheme, the parameter generation algorithm is no longer trivial. What it does is it runs the key generation algorithm here to get a public secret key pair. Then it sets the parameters to the public key and returns that. So what this is doing is it's saying all users know this public key, and that's somehow going to be used in the committal scheme. One can ask here, but what happens to the secret key? Well, it's forgotten. We imagine this is run by some trusted entity. It does this, it publishes this public key, and then it dies, and the secret key is never used, never visible to anyone. However, the fact that the secret key exists, as we're going to see, is important for arguing security. How do you commit to a message with this parameters, which are now the public key? If you remember earlier in the symmetric case, committal had picked an encryption key at random. It no longer does that. It's going to use PK. But the encryption algorithm is randomized, and what it's going to do is it's going to explicitly, as we saw on the prior slide, pick that randomness so that it has a name for it and it knows what it is, and it calls that K. Now it can encrypt the message with that randomness, which is equivalent to the usual encryption. It returns the ciphertext as the committal, and it returns these coins as the decommittal key. When you want to verify, you have the parameters, which are the public key, a committal and a claimed message, and a claimed decommittal key. So how do you check that they match up? There's first a trivial check. You make sure that this is in the correct space. And if that passes, what you do is you don't, like in the symmetric case, try to do some decryption. You actually do re-encryption. You encrypt with this public key the message, and you see you get back the ciphertext. But in general, this operation is randomized. You can't re-encrypt the message and get back the same thing. But you can if you know the coins. So this algorithm with its two arguments is deterministic. So you can reapply it and see if you get back the ciphertext. So that's it. So now let's again check security. Well, hiding has worked just like in the symmetric case. If you look at the committal, it's just an asymmetric ciphertext produced by this encryption algorithm with proper random coins. So you're exactly covered by the INDCPA assumption on this scheme. The adversary is just looking at encrypted messages. The problem earlier had been binding, but it turns out that we've solved that. So, and why have we solved that? Because the goal of the adversary in violating binding would be to create a ciphertext with two different decryptions. Relative to the one public key, it has to find two different messages which both encrypt to this ciphertext. But that's not only hard to do, it's actually impossible. Why is that? Because of the correct decryption requirement, not for any reason of security, but because we know that decryption reverses encryption. So if you have this ciphertext, there's only one message it can possibly decrypt to, the one that you would get by decrypting under the secret key. I don't have to perform the decryption to make the claim that that is the case. It's just a mathematical fact. Algorithmically, we don't do any decryption anywhere. But the fact that it's possible tells us that two different messages can't possibly map to the same ciphertext. And that gives us the binding condition. So we now have a good method, but still one might see that it's relatively inefficient because it's using public key crypto, and that's slower than symmetric crypto by orders of magnitude. Can we do it with just some block ciphers and hashing type thing? So let's try with a hash function. So we take like SHA-256, and here's how we build our commitment scheme. The parameters are empty. When you want to commit to message M, you simply hash it. And you could set the decommittal key to the message itself, and you return the committal and the decommittal key. How do you verify that hash? Well, what is supplied here are the committal and a claimed message and key pair. So what the algorithm does is it just hashes the message and sees if it gets back the committal. It just checks this equation. And for good measure also that the key provided is accurate, which is that it equals the message. So that's another scheme. Does this one work? Well, the nice thing about this one is we do get the binding property quite easily under the usual assumption on the hash function, which is collision resistance. So violating binding would mean finding collisions in the hash function. It would amount to finding two different messages that hash to the same C, because that would mean that they can both be opened to C. So that's good, but it's not going to be hiding. And one way to see that is to remember that our hiding requirement is very strong. It's an INDCPA style hiding. It's not saying something like, can you recover the message from the committal, even though even that actually isn't in fact met. So now here's an example to see why it isn't hiding. We can just look at the usage in the internet casino. There the message was a guess, but everyone knows that the guess has a very small range. It's just a number between 1 and 100. So when the adversary or the casino gets the committal, and it's trying to figure out the message. Remember, this is the ciphertext. It's supposed to encrypt the message. It can actually figure it out. How does it do that? Well, it just cycles through all possible values of the message and hashes each of them and sees when it gets back this committal. And whenever it does, it has the message. And fundamentally now looking back, we see what the problem is. No privacy is really possible in the INDCPA sense without randomization. And this whole thing is deterministic. So we really can't be expecting much of anything in the way of privacy. But we learned something, which is that we figured out that you can map the binding quite easily to collision resistance. So here's a better scheme that is in fact the one we saw in our very first crypto rendition of the Internet Protocol. What it does is it just randomizes the hash function before hashing the message. So you pick a random 128-bit string as the key, you prepend that to the message, and then you hash to get the committal. And you return the committal and the key. When you need to verify, you would take the committal, the claimed message, and the key, and just check. You would hash the key and the message and see that you get back the committal value. And the claim is that this, by and large, works, at least if you have a good hash function. The prior problem of being able to violate privacy will go away because you cannot rehash candidate messages. The reason you cannot is you don't have the key. So you don't know what to put here when you're rehashing. And on the other hand, the binding continues to follow from collision resistance. It turns out that commitment schemes are extremely widely used. It's a basic building block in all kinds of different crypto protocols, including zero-knowledge proofs. So people study them a lot and they build lots and lots of different ones. Okay, so as indicated at the beginning, this is just kind of a tour of example protocols. So let's go to another example, which is actually kind of related to the prior one. So all through the class, we've seen Alice and Bob cooperating to prevent some adversary from eavesdropping on their communications or impersonating them and so forth. But then things went wrong and they aren't getting along, and now they're getting divorced. They want to decide who keeps the car. It was pretty expensive. And being cryptographers, they agree that they're just going to decide this by a coin flip. They're willing to flip a coin and the winner keeps the car. Now, if they were co-located, that may be quite easy. Flip a coin, see if it lands heads or tails. The problem is, by now Alice has moved to New York and Bob is in Los Angeles. So the question is, can you help them out by showing how they can flip a coin fairly amongst the two of them? So Alice suggests the following. She says, I'll flip a coin and I'll send you the outcome. And Bob looks at that and he's not too happy. And why is that? Because, well, he doesn't quite trust Alice, right? He doesn't know whether she's going to really flip a coin or just pick it to be whatever outcome she needs to get the car. So what we're looking for is something that's fair. Somehow neither party can influence the outcome. And we can do that in some ways by seeing this as a special case of the internet casino in which you're trying to guess a single bit. Or in a slightly different perspective, you get the following protocol. It uses a commitment scheme, so we're going to again leverage that same primitive. What Alice does is she picks a random bit, little a. But that's not going to be the coin, and she doesn't send it to Bob. Instead, she commits to it. So she runs the committal algorithm on A and gets a committal and a decommittal key, and she sends the committal over. So Bob now gets this ciphertext, and he doesn't actually know what A is. Bob picks his own bit, little b, and sends that over in the clear. And now Alice opens up. She says, okay, here's what was in my committal, and here's the proof in the form of the decommittal key. Bob checks that this is correct. He checks that if he runs verification on that committal and the claimed contents and the key, it gets back to 1. And then if all this works out, he knows now both A and B, and so does Alice. She had A over here, B over here. And they both agree that the XOR of A and B is the result of the coin flip. and that's what they'll use to decide who keeps the car. And the claim is that this coin flip is fair. Neither party can actually control it. So if Alice thinks that she wants the coin to come out a certain way, she's not able to do that because she has to pick A here before she knows what B is. And since she's committed to it, she can't sort of change her mind later. So A does not depend on B. On the other hand, B doesn't depend on A because all Bob sees here is the committal and it's hiding. So the hiding property prevents Bob from cheating, the binding property prevents Alice from cheating, and you basically get a fair coin. We could write that with the specific commitment scheme we saw earlier if you want something concrete that you can directly implement. And that's all that this does. It just shows you what happens if we plug in the hash-based commitment scheme and rewrite the protocol.